I get my timer ready. Okay, let me just make sure this. Okay. Okay. Okay, I'm gonna turn down the music and do it. Okay, hello everyone. Again, welcome to Astronomy on Tap, October. Happy Halloween. It's good to see you all. So I start every Astro on Tap like this, but tonight is a very special Astro on Tap because, I mean, not only do we have Tobin Wainer from the University of Washington giving a talk, but also we have the Astronomy Department's visiting colloquium speaker, Dr. Chris Moore, here to give a talk all the way from the Harvard CFA in Boston. Okay. But before we get to either of our fantastic speakers of the evening, we are going to start this Astro on Tap the way we always do, with trivia. And so just a reminder, I'm going to put up 10 trivia questions. I'll leave them on the screen for 30 seconds apiece for you to get your answers down. At the end, I will go back through all of the questions, but only for 15 seconds apiece to give you a second chance to get your answer down. All right, so with that, we're going to get started with trivia. I'm going to turn these so quiet. It's too quiet. People are really focused on the trivia. Terrified. So focused on the trivia. You ready to collect the trivia sheets? Okay. Get their trivia answers down. I said, did everyone get their trivia answers down? Thank you. Okay, so you can bring your trivia sheets and golf pencils, don't forget the golf pencils, to either V or Ben down here at the front, please, while we get our speaker set up. Thank you so much for participating in trivia. At this time, it is my pleasure to introduce our first speaker of the evening, and then I will turn the music off, I swear. So at this time, I want to welcome Tobin Wainer up here. Tobin is a graduate student at the University of Washington's Astronomy Department. Tobin graduated from the University of Utah with his bachelor's in Physics and Astronomy, and he is interested in stellar clusters and how stars form. So with that, I will turn it over to Tobin.
Thanks, Megan. Yeah, so my name is Tobin Wainer, and I'm here to tell you a little about how the stars that we see in the night sky formed. And I'm here to do that because I think that star formation gives us some of the most amazing images in all of astronomy, like this one, or this image here, which was taken with the James Webb Space Telescope not too terribly long ago. But also because I really believe that origin stories are important. And in order to really truly understand something, we have to know where it came from. And so on that note, my origin story is that I grew up in a really small town in the middle of nowhere, Utah. Moab, Utah. Shout out to the people online listening from there right now. So here's a picture from home. And as you can see, we can see the stars in the night sky incredibly well. And so growing up, I was able to kind of look up and see stars, see constellations, and that is what inspired me to try and do that for a living. And so on that note, when I tell people that I study the stars for a living, the first thing that they ask me is, what's your sign? And I say, no, astronomy. And then the second question that they ask is what my favorite constellation is. And my favorite constellation is Cassiopeia. And that's because if you look kind of closely and you tilt it just a little bit, it looks like a W. My last name is Wainer. W for Wainer, right? My constellation. But also, if you throw a U in front of it, UW, go Huskies. But a little bit more importantly, Cassiopeia is one of my favorite constellations because it has this triangle that points to a very significant astronomical object. And that astronomical object is this guy, Andromeda. And I've done a lot of my career studying the stellar populations and the stars in Andromeda. But historically, Andromeda is a really important astronomical object because it was the first ever external galaxy that was discovered other than the Milky Way. And it was actually Edwin Hubble who was looking at this little fuzzball in the sky. And it was believed to be some kind of nebula. We weren't sure what was going on. And in 1923, he saw a variable star in this nebula. And the variable star he saw was a Cepheid variable, which is a really cool type of star that will actually pulsate. So it will get brighter and dimmer very rhythmically. And you can time out how long it takes for the star to complete one full pulsation. And the brighter the star is, the longer it takes for the Cepheid variable to complete one full pulsation. And this is something called the period luminosity relationship. So the brighter something is, the longer it takes to complete one full pulsation. And from these two measurements, knowing how bright the object intrinsically was, and seeing how bright he saw the thing in the night sky to be, he was able to determine the distance to this galaxy. And the distance is around 2.5 million light years away, something that is way more than the edge of the galaxy, and at the time, way more than anything that had been discovered up to that point. And so, because we were able to determine that there were, in fact, other galaxies other than our own, our understanding of the universe expanded tremendously. But the origin story for the constellation Cassiopeia goes back to Greek mythology, where Cassiopeia once boasted that she was more beautiful than 50 sea nymphs fathered by the Titan Nereus. And the sea nymphs were not too happy about this. So they went to Poseidon and said, you have to punish this blasphemy. And so Poseidon, then the myth goes that Poseidon cast Cassiopeia up into the night sky as punishment for her vanity. And this is typically how we like to think of the constellations and their Greek names coming to be. There's a story associated with each one of them. But the ancient Greeks and I, seeing a W, aren't the only cultures that look up into the night sky and see a very specific pattern of stars. More specifically, the Sami people of northeastern Europe, when they look up, they see a W, but they see elk antlers. And the Chetny people, thousands of miles away in Siberia, see the antlers not of a deer, but of a reindeer, which is native to their homelands. In Navajo astronomy, who inhabit the lands which I grew up on in Utah, they see the constellation of the female revolving one, who gives power to the home. Instead of a bow and arrow, her tools are her grinding stone and her stirring sticks, ensuring that the home is always taken care of. So all across human history, when we have looked at this group of stars, we've come up with an origin story on how they got there and why they are there, and we're looking for meaning. But actually, if we deproject the distances to each one of these stars individually, we can see that the pattern that they hold is actually due to our privileged vantage point here on Earth. And instead, each one of these stars is a different distance and a different age. If we go to the star at the upper left-hand corner of the W, the star Sergin, it's a truly massive star, about 10 times bigger than our own sun, and only 15 million years old. The star that is the furthest away is only 8 million years old and 17 times more massive than our sun. 8 million years ago, the Earth was just beginning to plunge into one of its ice ages as this star was beginning its own journey. The middle star in the W is actually not a single star, but two. The first star is about 2 times the mass of the sun, and it has a companion, a very dim companion that takes 800 days to go all the way around. And by far, the closest of these stars to us is also the oldest and the smallest, very comparable to our own sun. So when we look at each one of these stars, they didn't form in the pattern that we see them in the W. They have their own unique origin story that is entirely independent of the other members of the constellation. And because of this, and because of our current position in time, we can't look back and see when each one of these stars was formed. Kind of like here in Seattle, we have this massive monolith down to our south. We weren't here to see how this guy came to be. We didn't see the volcanic uplift. We have to use the tools at our disposal at our current moment in time in order to measure how these things came to be. And so these same types of tools can be applied to the stars and applied to our cosmos. So when we're trying to look at the stars in the night sky and understand where they came to be, we have one star in particular that is a lot easier to study than any other star in the night sky, and that is our sun. And it's because it's the closest. The sun has been studied for centuries. But tonight, I want to highlight the work of one astronomer, Cecilia Payne-Kapashkin, who was the first astronomer to actually determine what the sun was made of. And she did this by using a technique that is still used in astronomy today called the absorption spectra. Essentially, you split up the light that is coming from the star into as many different passbands as you can see, kind of like a prism. And the way that the light interacts with specific atoms or elements can tell you the elemental abundance in the star. And so Cecilia did this in 1929 and was able to understand that 90% of the sun is hydrogen and around 8% of the sun is helium. And this groundbreaking work was initially rejected because it went against the current scientific mythology of the time, which was that there was no significant elemental difference between the sun and that here on Earth. And it was her PhD advisor that then decided and convinced her not to publish her work, and then 4 years later, claimed this work as his own and published a paper doing the very same thing. And it wasn't until years later that Cecilia got the recognition that she deserved for her truly amazing work. But because of this groundbreaking work, we are able to understand that the sun and all stars, not just the sun, are 90% hydrogen. And hydrogen is the most simple element in the universe. It is a proton and an electron. But another groundbreaking feat that Cecilia was able to do was able to come up with a classification system for the stars based on their temperature. And so she was able to measure the temperature in the stars and found out that the internal temperature of the sun was around 27 million degrees Fahrenheit. And at temperatures that extreme, what happens to our little hydrogen atom, which is a proton and an electron, is the temperature strips away the electron entirely and leaves us with just a proton. So inside of the sun, because it is so hot, we'd have a lot of free-floating protons and a bunch of free-floating electrons. And protons are two positively charged particles. And when you try and push two positively charged particles together, they don't want to go together. Similar to what happens when you try and push two ends of a magnet close together. There's a magnetic force in between the two that repels them. In order to overcome this magnetic force, you need a lot of energy. And specifically, this energy manifests itself in a process called nuclear fusion. And that's what happens when you have many protons being shoved together to form hydrogen. And as I mentioned, the protons don't necessarily want to do this, but when they're under such immense pressure, it forces them together. And the energy that is expelled from this chemical reaction is equal to about 3 sticks of dynamite. But inside of the sun, there's a lot more than 2 protons going together to form 1 helium atom. In fact, there are 10 to the 37 hydrogen protons, approximately, enough to be expel the force of 91 billion nuclear bombs every single second. So the other thing that we know about the sun is that it is still there, right? We can look up into the sky and see the sun, which means that these nuclear explosions that are going on down in the core aren't entirely destroying the star. This means that the star has to be in something called hydrostatic equilibrium. So the outward force from the core has to be directly equal to the inward force of gravity collapsing on it in order for it to be a stable body in the sky. Okay, so now that we know what the sun and the stars are made of, and we know kind of what's going on inside of them, and we know that they are still there, now we can start to pontificate on how they got there in the first place. So, okay, we have a giant ball of hydrogen. That means that it must have started as a giant ball of hydrogen that then collapsed, and star stuff happened, and it made a star. And if we just take this like super simple assumption about how it got there, it turns out to be not too terribly far off from the truth, right? So if we take our toy model and bring back in that amazing picture of star formation that I showed at the beginning of this talk, this is actually a molecular hydrogen cloud, or a GMC, giant molecular cloud. Molecular means that the element is still hydrogen, it's just molecular hydrogen. It means that it has its electrons still, and it is coupled together with a buddy hydrogen to form 2, H2. That's what these giant clouds are made of, molecular hydrogen. But in order for the hydrogen to couple together, in order for it to stick together, in order for it to have a buddy, it has to be very cold, and we need very cold temperatures. Okay, so we have a cold ball of hydrogen. And when we look at these giant molecular clouds, we can see that it's not just one single ball that collapsed into one single star. But instead, when we look at our molecular cloud here on the left, we can see that there's actually overdensities in the gas. And that's what's shown here. We're looking through the gas to look at exactly how much of that gas is located in a single place. And so here, we have a lot of gas, likely to form a big star. And over here, we see smaller amounts of gas, but still concentrated, that will then form smaller amounts or smaller stars. And so these giant molecular clouds are the birthplaces of many stars all at once. And I know that there's somebody out there that's like, wait a minute, what about physics? Does anybody know Newton's first law? Shout it out. Sure, which is? That's a different one. Specifically, Newton's first law states that an object in motion will stay in motion until acted upon by an outside force. Or you can flip that a little bit and say an object at rest will stay at rest until acted on by an outside force. So we have our very cold ball of hydrogen, and without any kind of outside force, our cold ball of hydrogen will stay a nice cold ball of hydrogen, and there will be no stars. And it was actually a very recent discovery that happened right around us that led us to overcome this answer. So what I've shown here is the sun and the star-forming regions that are all around us. And in the early 20s, or in 2020s, it was discovered that in all directions, everywhere we look, there was a very diffuse emission coming from everywhere. And we couldn't figure out what was going on. And we see all of this star formation going on around us, but not next to us. And it was actually determined that we are living inside of a bubble. And the origin of this bubble traces back about 15 million years to a massive supernova explosion that acted like a snowplow, pushing all of the material around it up, causing an overdensity, giving that catalyst to our nice ball of cold hydrogen, pushing it to gravitationally collapse and form stars. Now, the sun was not always where it is right now. We were actually traveling throughout the galaxy. And while the supernova occurred, the sun and us along here on Earth, 15 million years ago, were way over there, galactically speaking. We could see the supernova go off if we were around. And we actually traveled straight into this bubble, entering the bubble about 5 million years ago. And it is only because we are now currently inside of the bubble that we can see all of the star formation going on. Now, this has led astronomers to really kind of believe or pontificate on how bubbly the rest of the universe is, right? We live inside one. Are we special that we are found our way inside of this bubble? And it allowed us to kind of come up with this theory of star formation, which is called the star-to-star cycle. So we have our nice star-forming region here, our big old giant molecular cloud, which has collapsed to form both big stars and little stars. And at the end of the lifetimes of all of these stars, the stars release their material back into the surrounding area. The difference being that small stars like the sun release it in a very slow, gradual manner, while very large stars go supernova and push the material out, helping to form the next stars, the next generation of stars. And while we've done this in the Milky Way, this is kind of where the edge of current astronomy lies, in trying to really find these individual star-forming regions. And so to do this, we have to go to external galaxies to know if other galaxies do the same kind of formation. And that's where the breaking news is. And what my PI has done is got time on the James Webb Space Telescope and pointed it to local group galaxy, the Triangulum galaxy, which is really close to Andromeda, technically speaking, and tried to look at very young star-forming regions in this galaxy to try and see if there are actually bubbles going on in there. And what I'm about to show you is a proprietary image taken with the James Webb Space Telescope. And so when you're seeing a never-before-seen image, you need a little bit more of hype. So can I please get a little drum roll? So what we're looking at here is we're looking at one of the very youngest star clusters in the Triangulum galaxy taken with the James Webb Space Telescope. And so here are the youngest stars, these blue ones in here. But what's really amazing is that when you look at the outskirts of this region, you can see the different gases. And specifically, when you look close enough, you can see the individual bubbles here that were formed from the supernova explosions of the past that is jettisoning this star formation in this galaxy. Now, a little while ago, I mentioned that we have a very privileged point in time and in space. We live in the current. We can't see the star formation taking place actively. And so to kind of help remedy that, one of our best tools is a simulation. In other words, we take all of the physics that we can possibly understand, throw it into a computer, and then see if the simulation looks anything like what we see going on today. So here's one of the best current simulations of star formation made by Mike Grudich. And so we start with our nice ball of cold hydrogen. And when we play the image or the video, we can see the initial catalyst begin. And the simulation will show us that there are many different forms of stars that go on. Oh, cool. Let's play it. And so as the first stars form from our giant cold ball of hydrogen, we can actually begin to see that the star formation process is destructive, and that as these balls are collapsing, they're jettisoning different materials out, blowing out all of the gas in the region around them. So this happens due to jets in the part of the star formation, and also from different supernova explosions from the most massive stars finishing their lifetimes. And so what we're left with is once all of the gas is blown away by these different processes, both the stellar winds and the stellar feedback and the supernova explosions, we're left with a group of stars that have all formed from the same cloud at the same time. And this is what we like to call a star cluster. And a star cluster comes in many different kinds of forms. Yeah. Thank you, Megan. Yes, clap for Megan. Technology, we gotta love it. So the first type of star cluster is the easiest to see, and that's because it's the biggest, and that's a globular star cluster. These globular star clusters contain billions and billions of stars and are very old, likely just as old as the Milky Way galaxy. However, there's another kind of star cluster, an open cluster, like this one. This one is called the wild duck cluster. If you can figure why it's called that, please let me know. I want to know. But the wild duck cluster and all open clusters are a lot younger. It's a lot harder to pick out the member stars from the background field population. And specifically with these younger open clusters, we can study them to learn how a galaxy has evolved throughout time. And one of the really cool technological advances in the last 10 years or so has been the launch of the Gaia Space Telescope, which is a European-based telescope. And what's really amazing about this is not the images, so it doesn't get quite as much attention as Hubble or JWST, which gives us these amazing images to look at. But instead, what Gaia can do is it takes very, very precise measurements of a star's velocity. And so you can actually track exactly how fast a star is moving side to side, up and down, and most importantly, tangentially to us. And once we have these different measurements for all of the stars, specifically the ones in these young clusters, we can then trace back the orbits, and I have another video here, so we'll see if it actually plays. No. But we can actually trace back the orbits for every single one of the stars in a cluster and watch how they dynamically evolve throughout time. And for a big cluster like this one is an example of a globular cluster. If we follow the path of a single star throughout this video, we can see it going around and around, or we can see it flung from the cluster entirely. These big clusters have big gravitational wells. It's really hard for them to throw their stars out into space, and that is why we still see them 12 billion, 13 billion years after they form. But for a young cluster, they will begin to dissolve a lot more rapidly. And so once we are then looking at the stars in our constellation, we can realize that they had to go through this immense process of beginning as a hydrogen cloud, having some kind of spark ignite their gravitational collapse, being with their buddies for a very long time until the cluster entirely dissolves, leaving single stars throughout the sky. Yeah, no, it's okay. And so next time we're looking at some of these constellations, we can kind of think about all of these steps that had to happen in order for us to see them in the very unique patterns that we do. Thanks, and I will take questions. Yeah. I'm sorry, can you say that a little louder? Okay, yes. So the question is, does the star formation rate that we expect from simulations match what we observe? And so the very first simulations, absolutely not. No, they got it totally wrong. They were seeing way too many stars, and they didn't include some of these processes that I was talking about, like stellar winds, that would actually halt star formation, right? They would just continue star formation going until they used up all of the gas. But instead, it's actually a very inefficient process. Only about 10% of the gas that is in the cloud then gets converted into stars. And so now the star formation rate is a better approximator. And you can use the simulations to and this is why matching simulations to observation is really important, because you can't really understand the physics of your simulation if it doesn't actually match up with what you see in the universe. Yeah.
Any differences seen between like first generation stars that we can see with James Webb and third generation metal-rich stars that we see like our sun?
Yeah, so there's a lot of differences. As you mentioned, one of them is the chemical composition of these stars. I'm sorry. So the question was, are there a lot of differences between some of the very first stars that we can see and the ones that are just being formed now? And one of the biggest differences is in terms of the composition. So as we mentioned, the medium in which the stars collapse down into is a product of the generations of stars before them. And so the very first stars didn't have extra elements. Instead, they were just purely hydrogen and a little bit of helium left over from the Big Bang. Whereas now, the stars that are being formed now have a much higher chemical composition. In terms of the actual star formation rate, I don't think so, right? The star formation rate is believed to, the same process is still believed to go on with the first generation and the generation that's going on now. Yeah.
What factors prevent a globular cluster, one of the older structures, from just compressing on itself? Why does it remain in function instead of exploding?
That is a fantastic question. It has to do with, okay, yes, sorry, thanks. The question was, what prevents a globular cluster from collapsing down on itself? And it has to do with the fact that the gravitational well from any kind of object is not infinite, other than a black hole, which is infinite. But the gravitational well from the sun keeps all of the planets orbiting at a constant rate. And so you can think of it as the same type of mechanism that's going on. If we were to have a trampoline and place a bowling ball in the center that is a significant, that represents any kind of mass, right? That's the mass. The way that the trampoline bends is how the gravitational well is then enacted. And so just like all of the planets don't fall into the gravitational well of the sun, they continue in their orbital path around it. It's the same type of process for the globular cluster. So the planets can't escape the solar system unless they're given a specific kind of velocity or interaction, which happens for the stars in the cluster. They also don't fall in on themselves. Yeah, we'll go here. Yeah.
So do stars in the star forming region form different masses, and so what causes different stars to have different masses?
Yeah, so that's a great question. The question was, what causes the masses to, what causes the different masses of the stars to form in these different regions? And the answer is that there's typically a governing function, and it's called the initial mass function. And it says that preferentially, it is a lot easier to form smaller things than it is to form bigger things. So there's going to be around a factor of 1.3 more small things than there is big things. One more question, yeah. Yeah, so the question was, when we look around, do we see any of the stars that we believe to have come from the same stellar nursery as the sun? It's a great question, and I wish that we could trace back enough time to actually see the sun's molecular cloud that it formed in. It's believed that the sun is about 4 billion, 4.5 billion years old. In that amount of time, the sun has actually gone around the entire Milky Way galaxy a number of times. And all of the stars that were in our sun's stellar cluster are scattered throughout the galaxy. I wish we could know which ones they are, because I would point to it and say, hey, that's our brother, sister, etc. Yeah.
They found like 2 of them.
Okay.
Based on like motion and for chemistry and that kind of stuff.
Cool.
This is 2.
Yeah. All right, thanks.
You can give that to Chris, but then make sure to tell him not to turn it on yet.
Okay.
I'm gonna steal this from you. Thank you. Another round of applause to Tobin. That was fantastic. Okay, so at this point in time, I'm going to tell you all the trivia answers, and then I will announce the trivia winners. We have a 4-way tie for first place, and there are no second or third place winners. So with that, let's go through the trivia. This is the Cat's Paw Nebula. I cannot pronounce that. Answer D is the closest star-forming region to the Earth. It is true that we can see the jets coming from newly forming stars with telescopes, not with our eyes. Okay. In 1995, this picture from the Hubble Space Telescope of the Pillars of Creation was taken. We can see newborn stars with the infrared wavelength. Ariane 5 was the name of the rocket that launched JWST into space. I was going to guess homemade bottle rocket number 7. STS-125 is the name of the 2009 space shuttle mission that repaired and updated the Hubble Space Telescope. Nancy Grace Roman Space Telescope is not currently in space. It is true that it is impossible to do X-ray astronomy on Earth because our atmosphere absorbs X radiation. And the first optical photo of an exoplanet, Fomalhaut B, was one of the first achieved by a space telescope. So with that, let me announce the trivia winners. First up, we have Incredibly Dense. Well done. Well done. We have Wormhole Extreme. You guys don't sound very excited. You get a prize. Yes. And then we have Singularity. Woo! And International Base Station. Yes, well done. Okay, so you can come get your prize at the end of the second talk. So at this time, we're going to take like a 5 to 10 minute intermission, so you can go get a drink, go to the bathroom if you want, and then we will bring on our second and final speaker of the evening. Thank you.
I'm gonna make sure we're on Wi-Fi. I need to connect this. How is this on? Oh, right. We have to do this. Okay. This one? Connect. I can't tell. I think it is. Okay, can you play something? Okay, turn it off. I can't turn it off. He just startled me. Scared the shit out of me. Okay. That's like, that like made me sweat. Honestly. Yeah. Okay, to be ready. Let's see. I'm gonna see if the videos play on commands now. I think it's playing on commands. Okay. It says Harvard College Observatory. It says Harvard College Observatory. So, that's where we're going. Are you
Okay, welcome back everyone from the intermission. Hello. Hopefully you have all refilled your beers. At this time, it's my pleasure to invite our second and final speaker of the evening, Dr. Chris Moore. Chris works at the Harvard Center for Astrophysics. He has a dual appointment at the Smithsonian Astrophysical Observatory and the Harvard College Observatory. He's interested in the atmospheres of stars, and he builds, designs, and tests technology for future NASA missions with small satellites and rocket launches. So with that, I would like to invite Chris Moore.
Testing, 1, 2, 3. Can you hear me? If it's all right with you, I'll walk around. Is that okay? Yeah. thank you, Astronomy on Tap, Seattle, for having me today. I'm your guide on this adventure. So Tobin did a great job. It was kind of like a lecture. I'm a little different for today. It's more like a movie. So I hope you guys enjoy the movie. And today, like I mentioned before with Megan, we'll be speaking to you about launching astrophysics telescopes and detectors on rockets and satellites. And what you're seeing there actually happened. We'll get to that a little bit later. So as your host for today's journey, I'd like to introduce myself. My name is Chris Moore. As mentioned, I'm a researcher at the Harvard-Smithsonian Center for Astrophysics. I received my PhD from the University of Colorado Boulder a few years ago, working on ultraviolet coatings and the miniature X-ray solar spectrometer CubeSat, and that is a picture of myself holding the CubeSat. It is very, very small, as you can tell. It's so small I can hold it in your hand. But one of the aspects of our research group is to constrain how cool stars like the sun, relatively speaking, have an atmosphere that's much, much hotter than its surface. So that's like putting your hand to a light bulb and then moving your hand away from the light bulb and it getting hotter and hotter as you move your hand further and further, farther and farther away. We're still trying to figure out exactly how that's happening. We do understand the energy transport mechanism from the surface of the star, the sun, and lower mass stars up into the higher layers of the atmosphere, but we're not really sure how that energy gets to very, very small scales and then converted to random motions of particles, which is what we feel is heat. So like right here, this heat is really, really hot. I don't know who turned it on, but you did a great job. I saw that we were outside and I was a little concerned. I said, oh man, it's just Seattle. It makes like 50 degrees at night. So I'm able to bring my jacket. But then this heat, great job. As I mentioned before, I focus on stars, primarily the sun for right now because of some of the things that I will show you today. I wanted to get to O and B, so very hot, massive stars that don't live very long. They explode as supernovae, and they end up creating black holes and neutron stars, articulated by Tobin here. But then, some of the images I'll show you today. I started doing research on the sun, and I haven't been able to get away from it since. So hopefully after today, you'll think that the sun is a very, very, very cool star. And I focus on studying both the quiescence and eruptive heating processes in stars like the sun, which again, is one of my favorite stars. The star of the show for today is the sun. It's not like any other star that you've heard about because it's so close. Tobin mentioned this. Its proximity allows us to observe it in glorious detail that we cannot see other stars in such fabulous detail. Now, if I show the laser pointer right here, it's similar to the size of this blue pale dot. I know people in the back, they can't see this, but there's a blue pale dot right here. That's Earth, so we're pretty small. And Earth spans about, it takes 100 Earths to span the diameter of the sun. So we're very, very fortunate. For me personally, sometimes we think our lives are pretty important, and then I think about stuff like this. Like, man, I'm one little person on this one little dot in this one system around this one little star amongst all these other stars. And I just enjoy my life. Puts things in perspective. So there was a partial solar eclipse that happened in the United States the past weekend. Have any of you heard of that? Yeah. And so that was an annular eclipse. And so that's a unique situation where the moon passes directly in front of Earth, and it passes at such a distance where it's slightly smaller than the sun. And hence, you have this annulus of the sun that still is visible. So it's pretty cool to see. They call it the Ring of Fire. Back in 2017, I was fortunate to lead a tour to see the last total solar eclipse. There will be one next year in the spring, so please, if you have the opportunity, catch the path of totality. It looks something like this. Now, this isn't the highest quality video that I could display. This was from a colleague that I know, Jay Paskoff. He passed away, unfortunately, in the past year. But he was a solar eclipse chaser, so he would travel across the world to take video with his camera systems, just like this. And for myself personally, watching the solar eclipse live, and I don't know how many of you saw that in totality in 2017, when the visible photosphere disk of the sun is blocked by the moon, you see the extremities, the outer atmosphere, primarily called the corona. And you see the visible light from the photosphere being reflected or scattered off free electrons. And these free electrons are forced to stay around the large-scale magnetic field of the sun. And you see what we call like a dipolar structure. Tobin spoke a little bit about magnetic attraction, with electronic attraction in this case, with the proton-proton chain. But this is slightly different, this magnetic field, but you can put a bar magnet here and you see a similar effect with the north and the south poles. And you also see some structure near the equator of the sun. So in addition to these free electrons that are scattering light from the photosphere, you also have this decrease in intensity as you move further and further out. That's mostly due to dust particles that are also reflecting the visible light from the sun. So as you can see, the sun has many things that are happening that we can't see with our naked eye, or even if you take one of those solar telescopes and look at an H-alpha filter, you'll see different aspects of the atmosphere, but you will not see this. From Earth, we can only see this when there's a total solar eclipse. So that's a big dilemma. All right, so what do? What if I wanted to see the sun in a different lens, to a different view, in a different portion of the electromagnetic spectrum? Because we are only sensitive to a very small bandpass. Our eyes is only sensitive to a very small bandpass, the visible light portion. But there's all these other manifestations or flavors of light, from the radio waves that we listen to in the car, the microwave that we use to heat up our food, infrared, which is used primarily that I think about like infrared goggles, which I think are really cool. Ultraviolet light that people may try to put sunscreen on to block from the sun so they do not get skin cancer. X-rays when we go to the doctor to have our bones checked. Gamma rays, hopefully you never have to deal with gamma rays. They're pretty crazy, they're pretty violent. Yeah, spanning this entire spectrum of pure energy, which is light. So, question time for the audience. I'll give it away. This is the sun. This is a composite video. My question to you all, we just talked about the EM spectrum. What do you think is the EM spectrum portion of this video? Like, what are we looking at? We saw the sun in visible light. We saw how it appeared. This does not look like that. So I have an ultraviolet in the back. What else do I have?
X-ray.
X-rays. Okay, what else? Infrared.
I'm gonna go with gamma for fun.
Oh, gamma. Okay, so unfortunately it's not gamma. You need very, very energetic processes to create gamma. Now the sun does create gamma rays. It happens during a phenomenon called a solar flare, a solar eruption. You have a magnetic field rearranging itself. It accelerates particles, in this case ions, at very, very high velocities, and then you can have gamma rays. Infrared, the sun is always making infrared light, but it does not have a spatial pattern. X-rays, we will be talking about X-rays a little later. You're very close. Right. The sun, outer atmosphere, has plasma that's hot enough over a megakelvin, a million Kelvin, that creates copious X-rays in these regions here that appear very, very bright in this video. You can also see these transients happening. These are magnetic field, these are loops. That was a coronal mass ejection being jettisoned off into space. There's another eruption down here. There's another eruption over there. You didn't see all this in visible light, did you? You know the sun does this almost every day. Looks pretty boring, but when we look at different lenses, it looks very different. UV, you are correct, my man. That is right. So, I started seeing imagery like this. I started to investigate the solar atmospheric properties, and I haven't been able to leave since. So one day, Tobin, I'll go back and study maybe black holes or neutron stars, but as of right now, this is captivating to me. Hopefully it's captivating to you all. So that was a pretty wide field view of the sun. If we zoom into the atmosphere, and this is actual, these are actual observations now. These are not simulations, these are not HD movies. These are real observations taken with real telescopes observing the atmosphere of our closest star. That looks very, very different than what we typically see when we look outside of our window. And by the way, don't stare at the sun directly without special eyewear. So this is a video taken composite imageries from the sun and combined and false color coated. And that was an eruption, a solar flare, which had plasma jettisoned off into interplanetary space. This video is created by Miloslav Druckmuller and his team, and they have many of these videos on their website. You can see the plasma is cooler, that's black and red, floating back into the solar atmosphere, being pulled down by gravity and following down the magnetic field structure. These are deeper layers of the atmosphere here. Higher layers up are these white and purple regions. These are strong magnetic field lines protruding out of the sun, going back in, keeping charged particles around them, which are losing energy by emitting light. I have a question before questions even came up.
Well, because can you define composite imagery?
So we take images in many different band passes, let's say red, green, blue, and then we can combine them and overlap them so they're all co-spatial and co-temporal. And astronomers tend to trick people, right? We put false coloring. So it's not really red, it's not really blue, it's not really purplish. It's colors that our eyes can't even interpret. So we put them in visible light representations so we can envision what's occurring. And so I thought this was so cool, I'll play it again. Are you all cool with that? I never get tired of watching this. So to me, it looks like lava floating back down. And remember, this is our star, the sun. This is one of the more boring, mundane stars. So just think what's happening on all these other stars that are in our galaxy and in the universe. So one day, I would like to be a part of the team that actually images another star at similar resolution. You think that can happen?
Yeah.
One day? So one day, maybe in 2060, I'll come back to you, Washington, Seattle, Astronomy on Tap, and I'll say, look, we imaged the star. This is what it looks like. Yes, I have a question in the back.
How long did that video take to record? Is that like real time or sped up or slowed down?
So the question is, how long, what time scale is this eruption occurring on? So solar flares can span minutes and it can span hours. This is a smaller, medium-sized solar flare. This time scale for this is about 30 minutes, so it is sped up. If it was real time, we'd be sitting here all evening. So it's sped up to, you can see the good stuff. Are there any other questions? This is a question asking audience. There is another question. Yes.
If you were to like break this up into like regions, how significant in different band passes is the spectroscopic variation of spectral features in different regions of the sun?
Can you repeat that?
So if you broke this on into regions, like you broke it up into a coordinate grid, right, and you looked at different squares, how significant is, because this looks very dramatic, how significant is the variation in spectroscopic features of each imaginary box?
Spatially or just the features
Either way.
themselves? So what I understand from the question, and correct me if I'm wrong, the question was if you break the sun off into different regions and you look at different spectral components, what's the magnitude of the variation?
So if you spatially break, like let's put an imaginary coordinate grid in the sun, and you were to take little, to image it, take them apart into composite images, like single things, would there be a spectroscopic variation in all of these colors? It's like, are these colors representing any variation at the spectroscopic level?
The answer to your question is yes. He's asking what I understand.
Yeah.
So this is a false color composite image. There are intensities that are measured each of these three bands. So this is 304 angstroms, or 30.4 nanometers, 17.1 nanometers, 21.1 nanometers. This is helium, this is iron, and this is a kind of continuum mixed in with a little bit of iron. And from what I'm understanding is the contrast that we see. Is that linked to the intensity of each of these, or how prominent that feature is?
Yeah.
Yes, the answer is yes. But the thing is, in the real world, right, our eyes have a sensitivity curve, we're actually most sensitive to the green, and that's primarily through evolution, right? The sun has a maximum intensity near green, near 500 nanometers. So there's always some curve or sensitivity change as a function of wavelength. But yes, this is similar intensity scale for each of the band passes. So there's no funniness going on there. I think we have another question in the back. Yes, you?
Yeah, all right. When we're launching that, kind of hard to interpret. It reminds me a lot of like a water jet coming off the surface and then falling back and sizzling. What is this surface that I'm interpreting it as a surface? This material is falling back to the surface and then changing spectrum.
The question is what we're calling the surface or this region where it seems to be opaque and you cannot see any more features beneath it, correct? So light is created in a situation and it can stream in any direction. Now there can be directionality, and for our conversation here, let's just say there's a parcel of material, it emits light, it can go in some direction. And it will continue propagating unless it's acted upon or interacts with something else. So the light that we see here in the ultraviolet, and in this case, this is 171 and 211 angstroms, it's going to continue to propagate until there's some material that interacts with it and absorbs it and re-emits it in another direction. The mean free path is what that's called, how far on average before this light interacts with something else. It's pretty long, it's all the way to Earth in this situation. Now for this bandpass though, 304, it's cooler plasma, this is helium. The structure of how the abundance of helium changes as an altitude and the temperature structure of the sun as it changes in altitude, it leads to the fact that the electron that's coming from a high energy state down to a low energy state that makes this photon, that it likes to happen at this particular altitude with these temperatures and these characteristics. So the light we're seeing there is mapping a pretty narrow altitude. And all the emission that's happening behind it, deeper along the line of sight, is actually being absorbed by helium in the foreground. And then we're seeing the helium emitting closer to us. So that's the surface. And surfaces for stars is a tricky statement. So the photosphere for the sun is a region where, due to, again, changes in temperature and density as a function of altitude or some of the primary drivers, along with elemental abundance like Tobin mentioned, it's a state where hydrogen, which has one proton, one electron near the surface of the sun, we call the surface at that height, it attracts another electron. The temperature drops just enough so that an electron can be bound, a second electron, to the hydrogen atom. So this is called an H- ion. So this net negative charge, because it has two electrons for one proton. But the amount of energy that it takes to liberate that extra second electron is not a lot. It corresponds to infrared wavelengths. And the sun makes a lot of infrared light behind it, like before it, the light propagating along the direction. And so that's why the visible surface, we call it a surface, it's not really. It appears so sharp because it's a small range of heights where this H- ion can exist before another photon comes and then breaks it apart. And then when you go higher than that altitude, visible light that's created and then released, it can travel all the way to Earth almost uninhibited. And so that's the mean free path is almost 1 AU or longer, is how we would say that in scientific terms. And so that leads to this very sharp interface, invisible light, for the photosphere of sun, the sphere of light, photosphere. Now in the UV, as you saw, this leads to another question actually. So why do we need the moon to occult the bright disk? Is because it's about 1 billion more photons coming from the photosphere, the disk of the sun, than out here. That scattered component is fractional and mostly all of that light, not all of it, but a lot of it is coming from here. Scattering off those electrons, scattering off dust, but then there is gas, plasma, that's out here that also creates light, visible light. It's very, very, very dim though. And so it's very difficult to see. There are people who measure it. That was a great question. I have another question.
Yeah. For reference, can you tell us how close the Parker Solar Craft is to the sun?
So the question was, how close is Parker or Solar Probe? That's a satellite that's coming very close to the sun, and then in its perigee and then apogee goes pretty far away. I don't know the answer to that question. My old office mate works on Parker. A bunch of people actually at the Center for Astrophysics work on Parker. I don't know where it is right now. I have to go look it up. But if you go to Google, I'm pretty sure there's a web page that can show you where it is right now. There's another question. Yes.
When we see the video of the sun and the motion there, how much do we understand from first principles of what's going on there, such that when you come back in 2060 and report on another solar, would you expect to see anything different, or would you expect to see confirmation of what we know from our understanding?
The question was, when I come back in 2060 to show you how we've imaged another star, do we expect to see the same thing
Yeah.
from the sun?
Is our understanding of our sun such that we would expect to see the same thing in a extrasolar sun?
Based on our current understanding of our star, our sun, will we expect to see similar things on another star? If it's a star that's similar in age, about 4.5 billion years, similar in mass, similar in circumstellar environment, meaning there aren't any companions or things that have gas flowing into it, causing a change in the evolutionary state, because that can actually speed up the evolution of stars. It can also change the rotation rate of the star, which modifies these magnetic field structures, which can lead to more eruptions. It can lead to a very different external atmospheric state. I don't know. Hopefully it's different, or else if everything's the same, then we don't have a job, right? I like your question.
It depends.
It depends. All right. So this whole talk, we haven't even gotten to the point of this talk yet. We're so busy focusing on the sun, but that's great, because you guys think the sun is a cool star, it sounds like, right? So I did my job. I'm done. Going home. So that image, the imagery that you just saw in the ultraviolet light, that was not taken on the ground. In visible light, light from stars, the sun, and other sources can travel directly to the ground. That's why we see the sun right now. In radio waves, it's similar, but in the infrared and parts of the microwave, the composition of the atmosphere, mostly nitrogen, oxygen, carbon, hydrogen, absorb a lot of this light. Similarly, in the ultraviolet and the X-rays. For example, I was just speaking with one of the graduate students here. Our rule of thumb that we use in our lab, because we have vacuum systems, we evacuate a lot of the particles. And 1 kiloelectron photon will travel, if you had 100 of them, 90 of them will be absorbed within 1 inch. 10 of them will continue to propagate. Another way of saying that is 90% of the light will be absorbed at 1 kiloelectron volt in atmosphere. I mean, that's why we gotta go to space. Yeah, which is the whole point of this talk, right? So Earth's atmosphere absorbs most of the solar X-rays and the UV. And so we go to space and put stuff in space. Now, how do we do that? There's multitudes of ways. One way is with NASA sounding rockets. These are fairly short trips, 15 minutes in total. And here's a chart. It's kind of hard to see, so I'll just read off a few important parameters here. These are different types of rocket boosters that NASA and NASROC use to get to different altitudes. This is the highest that the rocket goes at apogee. These are parabolic trajectories, so it goes up and comes right back down. This is the time above a certain height of 100 kilometers, and this is a function of weight. So the heavier you are, you don't go up as high, and you don't last at that height as long. So these can go up to the International Space Station altitude, which is roughly 400 kilometers. The rockets that I work on now, we go to about 250 to 300 kilometers, depending on the mass and weight. And at the launch, this is an example of a launch at Poker Flat, Alaska. This is a really cool image that I just took from the NASA Sounding Rocket Handbook, and you can see the light trail. But you don't have to just settle for static images of rockets. I did bring some videos. Some videos of some rocket launches, a couple that I actually saw myself in person. Some of them, like this one. I was part of this research group. I was a first year grad student, so this is in 2013. This is at nighttime. These rockets can be fairly large. They're not the big Atlas V type of rockets or SpaceX rockets. These are smaller, 22-inch diameter or 17-inch diameter rockets. They're pretty tall though, 20, 30, 40, 50 feet in extent. There's rocket boosters, and yes, we have the audio. And so this is at White Sands Missile Range in New Mexico. So I was actually there for this launch. Again, I was a freshman, so I was joining a research group. I didn't work on this instrument, but I was part of the work that we did later. And so rocket was horizontal. The housing was pulled back on a rail, and then the rocket went vertical. The styrofoam to keep the scientific instruments cool. This is one of the rocket boosters. There's the second one to get off the rail, and that one takes you all the way to space. These things are pretty tall. And they also jump off the launch pad. And so if you blink or turn your head, you're going to miss it. Where? And so that was the second stage that just ignited it. So as you see, they're pretty fast. And it's a pretty violent ride. So if you have a satellite or instrument on board, you want to make sure it's mechanically, structurally, thermally, and vibrationally sound. Or else things will shake apart, they will break, and that is a problem for everyone on board. Right. So it's continuing up into space. We have the saturation problem here, so you can't see all the details. But it's pretty fast. So do you guys want to see what it's like to actually ride on the rocket? We have a question in the back. Yes. I can't speak for the second stage. The first stage, I know for sure, yes. So are you all ready? So this one is a visible, it's during the day. It's looking at the sun. So before we were looking at O and B type stars, so very massive stars at night. This is where we're looking at the sun. So it's the middle of the day around noon in White Sands and Missile Range. University of Colorado Boulder, LASP, Laboratory for Atmospheric and Space Physics, assembled this. It's pretty cool to watch. So we have altitude here. You can actually see the trajectory here. Again, it's parabolic. So we launch in the missile range. We land in the same missile range. You're going to see the velocity here. Before we get started, how long do you think it takes to get into space with one of these quick off the launch pad rockets? So this is a question for the audience. 30 seconds, we have 2 minutes. What else do we have? 60 seconds? Okay. Let's find out. So why do you think the rocket is spinning? For stabilization, that's correct. So we have cameras forward and aft, and this is actual audio that you're hearing on the rocket. So what do you think that sound is? Rocket motors, it's not the motor itself. What do you think?
Fuel going drag.
Drag. So you hear less and less of it. What's going on? Less air. So what was the sound? Air gushing out of the rocket, yes. So we're at about 50 seconds here. It's starting to get dark.
What altitude did you find space?
That's a good question. So it's a tricky question because the density as a function of altitude, it changes throughout the solar cycle. So more activity from the sun causes an ablation of the atmosphere. The atmosphere expands. So whatever we defined, it's going to vary over time. I would say, for me personally, around 100 kilometers altitude. I don't know if there is like a rule of thumb, but we can,
There are for astronauts. You have to go above a certain point to be considered an astronaut.
Right. Yeah.
that's true. We can look up what that altitude is. So the door opened up. There actually is a couple scientific instruments on board, and now it's slowing towards the sun. So there are thrusters on board, and it will take observations for about 5 minutes for scientific observations. So part of my PhD work was on one of these rockets. I had an instrument on board. There were probably 2 launches. One didn't work. It wasn't our fault. Someone in charge of NASROC, which is the company that handles this, put a gyroscope 90 degrees out of phase so the rocket actually off the side. So they have charges that explode and they go perpendicular to the vector of motion, and it separates the boosters. But we went back again a second time, and that one worked, and we got data, so I was happy. And so it's going to stare at the sun now. That's the sun. You can actually see Earth. This is pretty amazing to watch. I think the maximum velocity was near 2,000 meters a second. We're at 0 G now, 2 minutes and 14 seconds. And this is a pretty cool tracker. You'll see that it goes all the way up to apogee and then come down. The type of rocket for this was Terrier, Black Brant. Those are the booster names. And Laboratory for Atmospheric and Space Physics continues to do these launches to this day. We have rockets that we work with NASA Marshall Space Flight Center now. So I'm at the Center for Astrophysics. So we partner with them for some of our payloads. We have an X-ray telescope that's going on board and launching next year. I'll talk more about that. That will be in Alaska, March and April of 2024. So what I do want you to see some of the reentry, and then because this is going to be like 15 minutes, but I do want you to see some of the reentry, and then we'll move on to the next portion of the talk. Would any of you want to actually ride on that thing?
Yeah.
Like a yays and no's. Yeah, I agree. I wouldn't want to ride on that. That was a shaky ride. I have a question.
How many Gs?
I don't remember. I was somewhere around 9 to 10, what I recall, at the max.
50 miles is what NASA says. 50 miles is what NASA says. Like, being an astronaut, yeah, 50 miles.
So I'll show another launch soon. I went to Kennedy Space Center in Florida, and they have a simulator for the space shuttle. I don't know if any of you here have rode that. You rode. It was pretty violent. So I'm pretty sure this is way shakier than the rocket that takes you up on the space station for the space shuttle. And what's so amazing is when you're at these high altitudes, everything just looks so calm and peaceful and tranquil. So I think about astronauts, like what do they think about when they're up at the ISS and when they're looking out and looking at Earth, and everything's so peaceful and calm. But as we know, it can be hectic down here, especially driving to and from work, right? We have other questions while we're watching this, or everyone's just amazed.
The second rocket would have blown up. What would you have done for your PhD?
So fortunately, my entire the question was if the second rocket blew up, what would I have done for part of my dissertation work? Fortunately, my dissertation was twofold, but in that second fold, we actually, which I'll talk about in a little bit, have a CubeSat. So I also was fortunate to work on 2 rocket launches and then also 2 CubeSats. So there were backups to the backup to the backup. That's the thing though, there are PhD students whose rockets blow up or don't work, and they're kind of SOL. So for our UW PhD students, always have a backup. Very important. So we have about another minute before reentry starts. What do you, that's a question in the back.
Can you remind us what experiment was on this? What were you guys looking for?
So this one, here, is the Extreme Variability Experiment Under Flight. So EVE is what it stands for. It is an ultraviolet extreme ultraviolet spectrograph. So it graphs the spectra of UV light onto a detector. And this is to see the degradation for a satellite called the Solar Dynamics Observatory, which has been on orbit since 2009, I believe, and taking UV spectra of the sun. So my PhD advisor at Colorado, who's in charge of this, he was very smart. He said, hey, NASA, we need to just test and see how the satellite degrades over time. So we need to launch a rocket every other year. Because they built two of the same instrument, very identical, and they launched the identical one every 2 years to check for the degradation of the one in space. Because ultraviolet light is very, very powerful. It degrades your optics, it degrades your coatings, it degrades your detector sensitivity, and it's not linear. It's not really exponential because it can go through phases. It depends on the environment that the satellite's in. There's gas and gunk in space, believe it or not. And it can collect on the coldest things on a satellite, which tend to be the detectors, because you want to have low noise so they cool them. They can be cooled CCDs to -70 centigrade or -90 centigrade for some of the coldest ones. And that just collects all the dust, the dirt, the grime, carbon, hydrocarbons, silicones. Oh, looks like it stopped.
It is continued. Fix it.
Any other questions? No? So what do you think will happen when we start re-entry? It'll slow, what will slow down?
We'll hear the atmosphere get fired off.
Can you say that again?
I think we'll hear the atmosphere again.
We'll hear the atmosphere.
Rushing in.
Air will be rushing back into the rocket. What else do you think will happen?
You added a parachute, right?
We do have a parachute. So in the rocket that was cut down, we had a parachute, and that saved the instrumental payload. And so in the CubeSat that I'll mention, that same instrument was flown on that rocket.
So what tests did you put your instrument through to make it ready for the rocket?
Vibration tests. We shone X-ray light on it that had a known amount. So it's called synchrotron. These are electrons that are being accelerated by a magnet. And if you know the strength of the magnet, the structure of the system that the electrons are being orbiting around, you can accurately calculate the amount of photons and then this energy and X-rays that they are emitting. And so we went to the National Institute for Science and Technology in Gaithersburg, Maryland to do those tests. And as correctly said, we will start hearing air again. So that was, the audio was on that entire time. So just think if you're an astronaut, like in, I forget what movie was that? Where they were like lost in space and trying to get back? Gravity? Yeah, that's like a crazy thing. You don't hear anything, you're just floating in space. And so what's happening? What do you guys think? Why is it starting to wobble? That's on purpose, by the way.
Distribute the heat buildup.
Are you a scientist? So his answer was to distribute the heat, and that is correct. Because there are times when if that doesn't happen, and there's a uneven mass distribution and coefficient of thermal expansion for the materials on board, you can have the rocket bend and warp. That actually did happen. My first PhD advisor, that happened in his rocket on his dissertation. So he told me that he would train me so that would never happen for any of my rockets. Yeah, so we'll start tumbling, and this tumbling is intentional. So I mentioned before, after the second time the rocket works, we have our detector. It's an X-ray spectrometer that I worked on for part of my dissertation. We put it on these small satellites called CubeSats. By definition, 1 unit for the cube is 10 millimeter by 10 millimeter squared. And we stack
3 of these vertically. And we make MINX, stands for Miniature X-ray Solar Spectrometer CubeSat. It was the first CubeSat that was scientifically oriented, funded by NASA Heliophysics Division. People have been using CubeSats for years. They are mostly engineering technology demonstrations. there was a technology demonstration here with our attitude determination and control system. So how finally can we point at a region in space, in this case the sun, and how well can we know that and then keep it there? In addition to that, we were the first for heliophysics, so the sun, to put X-ray instruments on board and have those take quality observations. So there are two, they're twins, and both went to space. You can see our board stack here. You can see some of our electronics box down there. CubeSats are great for early career scientists to get real life training on something that's actually going to go to space and actually operate. And even though it's small, it is mighty. It is a fully functioning satellite. 40 plus graduate students, including myself on the mixed team, work to make this happen. And I commend all of them and thank all of them for their efforts. We have electrical power systems, because we have solar panels, which collects the radiant light from the sun and stores it in the battery. We have command and data handling from the motherboard, the brains of the spacecraft, with ultra-high frequency communications where we telemetry information back to Earth. And our antenna was a measuring tape. It's a piece of metal. All you need is electrons to move back and forth, and it'll radiate perpendicular to that motion of the electrons. And we have our X-ray scientific instruments on board. So someone asked, what do we do to make sure our instrument would work in space? There's a series of tests that we've done. This is a relatively short video that doesn't do it justice, but you'll see some of the testing that we did. And again, I mentioned it was a large team with multiple students. I was one of the few science students. I worked on part of the design of the X-ray instrument, characterization, writing a lot of the software to operate it. When we downlink the data, because I also worked on command and data handling and communicating with the satellite, reducing the data, doing scientific analysis with our data and other satellites' data. But a lot of the aerospace engineering students you'll see here, we're deploying satellite solar panels. We have to make sure they work, because you don't want your solar panels to not deploy. If they didn't deploy, it would just take a matter of time, because we had a heater that would heat and break the thread and it's spring loaded, so they would still spring open. This is the Yagi antenna that we just briefly showed, and I'll show it again later. We have trying to point to the sun. So we have a half sphere on flowing air, nitrogen basically, and it's free to move. And so we have reaction wheels on our spacecraft which can provide torque and make the spacecraft point in certain directions. So we have measuring tape, again, we wanted to make sure it went up vertical. It didn't do it that time, so that was a problem. And we also did this in vacuum to make sure that nothing stuck, essentially. And so this worked. So vacuum meaning about 1 million less particles within a steel container. And space is much less particles than that. We also want to test the pattern of radiation from our antennae. So we have a rotisserie pattern test. Like I mentioned before, it's an entire satellite. It's just very small. James Mason is a PhD student in the aerospace engineering department at the time who worked on the solar panels. Now, this is Boulder, Colorado, so you can see the beautiful Rocky Mountains in the background. We had to make sure the solar panels operated appropriately. You can reverse bias them and then actually make them get hot. You'll see that when they glow in the next few minutes. We have Kapton tape, special tape that's good for space hardware. We actually had to disassemble and reassemble our spacecraft a few times. We made a few mistakes. But that was the first mix. The second and third mix, we didn't have those same issues, so we didn't have to disassemble. We learned our lessons. And this is that reverse bias test that I mentioned before. So they're glowing red hot, making red light and infrared light. And also, James made the music for this video too. So this is the calibration at the National Institute for Standards and Technology that I mentioned earlier. synchrotron X-ray radiation, which can cause cancer. So there was a bunch of training we had to do before we went inside, and there was huge lead walls that we had to stay behind. And when you drop the gate, it's like, so you have to get out. If you do not get out when they inject the beam with electrons, you're in trouble. We do all this for science, right? There's aluminum tape also on the sides, and this is to reflect a lot of the UV light, because the UV light will be absorbed by the metal, and it'll via something called the photoelectric effect. It'll make all these electrons shoot off, and that causes a charge, and we don't want that in space. You also have to make sure it's really clean, so no dust. And at being in Boulder, there are a few former astronauts that actually work at the University of Colorado in the Aerospace Engineering Sciences Department. My PhD is in astrophysics though, but the majority of the students that worked on this project were in aerospace. And so he was signing anything for us. But what was really cool for us is we signed our names on the side of Minx. It was laser engraved. So it lived forever until it didn't. When Minx re-entered, it burned up and but like I said, it was a multitude of people that contributed. I think there's a question in the back. So NASA covered that cost for us through the grant. So I don't know exactly how much it cost NASA to do it. And we were a ride-along, so we did not drive the launch schedule. We just sat in the fairing in a container. And we went down to Kennedy Space Flight Center. So that's myself, James Mason, and at Kennedy. Oh, sorry about that.
4, 3.
So I don't know how much this cost them, but they negotiated with Orbital ATK. And this is the huge rockets that you guys hear about all the time. These are the ones that take forever. You're looking at it, and I was there for this too. And I'm like, is this thing ever going to get up off the ground? Just waiting. I got spoiled by watching the sounding rockets because they just go. And this one, I was still watching, and we're like, wow, it's really going. But once it gets moving, it actually is going. And another contrast to the sounding rockets, they're parabolic trajectories. So they go up and they land inside the same missile range. These, if you've been there, they actually go downrange. You actually can see it when you're looking pretty high up. That you can actually see it going sideways, getting prepared to orbit.
42 seconds into flight.
Question. So the question is, as a scientist, how many opportunities are there in a year for us to launch things? The answer to that is, it depends. So NASA has calls. They ask the scientific community, we have an opportunity to launch a satellite, let's say 5 years from now. We have a certain size of a payload for your instrument to be, power constraints, vibration constraints, telemetry constraints, mass constraints, all of these things. Scientific community, there's astrophysics, heliophysics, planetary science, earth science. We all kind of like put in proposals and battle it out with other professionals in the field that review it. They rank the proposals, NASA sees the ranking and appends an order, and then based on NASA's priorities at that time, they give the funds to 3 or 4 of them. It's called Phase A. So in Phase A, you said you were going to do something in your proposal. NASA's saying, okay, you said you can do this. Now we're giving you 9 months to show proof that you can do it. And this is all pen and pad, talking with your vendors, showing simulations and model results. You're not buying any equipment, you're not cutting, you're not building anything yet. That's the next phase. So NASA typically down selects to 1 or 2 after that phase. So you could have 20 proposals go in, 4 get selected for the first phase, Phase A, 1 or 2 go to Phase B. And then you continue to refine your design, and Phase C is when you start buying this. So it's a process. And then NASA typically handles the cost of the launch vehicle. You can negotiate when you need to launch, where you need to launch, the orbit you need to go into.
3.
But yeah, so Minx CubeSats were launched. This is the first version. And then they were deployed from the International Space Station. And so astronauts, they take, they're on 90-minute orbits. The sun, they see the sun every 90 minutes, so they're not programmed the same way we are here on Earth. So when this launch happened, it was in Boulder, Colorado, it was 3 a.m. So we're sitting at our facility at LASP, We're about to go up and run up to the communications room to start communicating with our Yagi antenna to our CubeSat, because we know at some point this is going to happen. So I'm like half asleep, right? And I'm watching this and I see this. I said, no! The CubeSat's going to crash into Earth. And then I started thinking, and my physics brain took over. I said, oh, it's going to orbit. We're all good. It was like a brief second, like very quick. Because when you look at it, you're like, oh, I was like, they said we were going to deploy it. I didn't know they were going to shoot it at the ground. I was like, wow. So fortunately, it did orbit, right? And for that particular orbit, it lasted 1 year, and then it eventually disintegrated in the atmosphere. But that was part of the plan. And we had to make sure all the components were of a certain density, and if it was over above, like a tungsten, for example, was pretty dense material. We had to make sure we had a less mass than a certain amount of tungsten because it needs to disintegrate and not like hit someone in the head when it deorbits. And so we had to make sure all those checks were in place. And so this is, again, actual imagery. It's photographs taken from the astronauts. So I don't show this often. You guys are getting some of the good stuff. I was looking through my photos when they said, you're giving astronomy on Talk. And I said, what can I show them that people don't typically get to see? And this is one of those things. So you can see the Japanese arm. It was a Japanese astronaut that controlled it. There was an American that actually took these photos, European Space Agency astronaut that actually took these photos. And this is the deployer. And these are the solar panels. It's pretty cool. And so this is another CubeSat that came out after ours. This is a pair of other CubeSats, so you can see what they look like. And this is our CubeSats. The second one here is Minx 1. This is a cadre from the University of Michigan. And these are the solar panels. And you see the Earth in the background. It's pretty cool, right? And then looking down, look how beautiful Earth is. Does anyone, I don't know where this is. Does anyone? So we got to get a bid in for San Francisco here. Does anyone know where this is? I don't know where it is. It's got to be amazing for the astronauts because they're looking down and they see the terrain. And there aren't any borders, right? They just see land. It's kind of tricky. And then here's a zoom in. Our CubeSat's in the back. And again, looking down at Earth, this is our CubeSat, the second one over here. So Minx was going away. And so we did a mad dash, ran to the computers to start communicating with our CubeSat. We're in Boulder, Colorado. Again, this is the Yagi antennas. This is me climbing on the back. One of our colleagues trying to fix the issues we had with our antenna. So we're actually doing work, right? We're actually like controlling everything. It was a lot of work. It was a lot of work. You have to be dedicated because this was like a 3-year process. So we're doing it again at Harvard. We're crazy, right? We just keep doing this over and over and over. So we have another small sat that we're proposing to do similar things, and this small sat is much larger. And like I mentioned, we actually had to communicate with our CubeSat directly. Nowadays, people actually outsource that responsibility to a company that actually communicates and sends telemetry data, collects the telemetry data down and sends uplinks to your CubeSat now. So we had to do a lot of simulations and figure out where would our CubeSat be, when would it be there, how long are the passes, do we have line of sight, and if so, what's the strength of the signal, how many packets could we downlink. We had to plan all this out, and for the first couple of months, we actually would wake up, and these passes would change during the day, so sometimes it'd be at midnight, 4 in the morning, 9 a.m. Eventually, we automated everything. Right, we wanted to just make sure everything was working for the first couple of months, and then we automated everything. So then we didn't have to wake up early anymore. And so this is one of the softwares that showed us our CubeSat and when we could communicate with it at Boulder. And University of Michigan had a similar radio bandpass with their CubeSat cadre, so we had to make sure we didn't interfere with theirs. And so that was a little tricky. So it was a lot of coordination that took place. Here's another simulation, which just look, it didn't work. But anyway, it's much, much faster. And this is from the sun's point of view, looking at Earth. The other one, Earth was still. And this is our CubeSat's orbit and the sun spinning. It's pretty fast. I mean, this is a quarter of a second is a day. So that's pretty fast in terms of the simulation. And so our research program, like I mentioned before, we work on a multitude of things. One of the things relevant for this talk are the detectors and the X-ray optics that we work on. We're putting them on a NASA sounding rocket that's launching in March of 2024. We have X-ray imagery. So unlike visible light optics, like the mirror you see in the bathroom, X-rays will go straight through that. But like a rock skipping off of a pond, when you throw it at an angle, that's how we reflect the X-rays off of metallic mirrors. So we do the same thing here. We have a paraboloid and then hyperboloid. So first mirror, secondary mirror, and it focuses at our detector. This is just an illustration. I didn't want to like show some of the ITAR stuff all over YouTube. And so like I mentioned before, we'll be at Parker Flats in Alaska, and we have to go there instead of White Sands because we're waiting for a solar flare and eruption, and then we have 2 rockets launching sequentially. And they're on 2 Black Brant 9 launchers. We have a land recovery, thank God, and we can just sit there and wait. And it's gonna be pretty fun, pretty cool. So I wanna thank you all for your time, and then I'll answer some more questions. So first, we have my man in the back, and then we'll come to you, and then to you.
Yeah, so it looks like you have about a month for that launch window. How confident are you guys that you're going to get a good solar flare?
We just have our fingers crossed. Now, there is some science that went into it. There's an 11-year solar cycle where between 11 years, you have not many solar flares happening, and then not many solar flares happening again. So within a 5-year span, there's many solar flares happening. We're coming up near the peak of that. So we should be getting like 1 a week. So we shouldn't have to stay there for the whole month and a half. I'm actually hoping we don't have to stay longer than a week, because it's going to be a long time in Alaska. But we do this for science, right? I know my grad students, they understand me, they feel me, right? Question over here. The question is, are the solar panels sun tracking? Which solar panels? On the CubeSats. So are the solar panels on the CubeSat sun tracking? What we do is we actually pitch and yaw and roll the CubeSats such that the solar panels are always pointed at the sun. There are reaction wheels that are on 3 axes, and they spin and they provide torque. We also have magnetic torque rods, which uses Earth's magnetic field to orient the spacecraft. And our science instruments are pointed in the same direction as the solar panels, because our scientific objective is to measure X-rays from the sun for the MINX CubeSats. There's actually 3 CubeSats. I just showed 1 here today. Next question.
Do you anticipate CubeSats are going to continue to be a bigger part of space-based research? Because I imagine having the small detector would be limiting. I'm curious if your capabilities are growing quickly there.
So the question, as I understand it, is do I believe that CubeSats will continue to play a role in the scientific objective of NASA and astrophysicists and continue to expand?
Yeah.
Probably not. One of the reasons that I personally say that, working on 3 CubeSats so far, 2 intimately, and the 3rd by helping the grad students and the postdocs at CU Boulder. CubeSats have like a 50%, science-oriented CubeSats have like a 50% success rate. Meaning like getting to an orbit and working on orbits. MINX 1 worked the whole time. It was a pain in the butt, but it worked. The second MINX, there was after it launched, after 2 months on orbit, taking science data, it was supposed to last for 5 years. It was a sun synchronous orbit, so we did not go to the ISS, we went somewhere else. Telemetry mistake. Someone sent a command they weren't supposed to send, and we had a surge in power, and so we believe the CubeSat started tumbling, and we haven't heard from it since. The 3rd CubeSat worked, though. So that's right along with that. 1 works, 1 doesn't work, 1 works. The next one's not going to work, right? And there are other CubeSats that I know that I won't say here, right? They didn't work. So it's about a 50% success rate. Many scientists get excited. Oh, CubeSats, they're amazing, right? And they think they're going to solve almost all of their scientific questions just with 1 CubeSat, and that's unlikely to be the case. These CubeSats are powerful and mighty to fill a particular void in a particular niche. And that's what we did with our CubeSats. I still use satellite data from other large satellites for my dissertation and for continued research. It's good to enhance the observatories we already have. But I think just because of that, it's, no. One more question?
All right, so given the, whatever, 10, 11-year solar cycles, so 5 years from now, is that just like extended proposal writing season, or is there good stuff to be collected from the sun's relatively quiet?
So the question is, because there's an 11-year solar cycle and there's a lull period in solar activity, do scientists just kind of write proposals and don't really do much other science? Well, a lot of scientists, they write the papers for the science observations that were taken during solar maximum. Well, for me, I'm more of a flexible scientist. I study flares, I study eruptions, but if you remember, we go back to these videos of the sun, and there was a question about this earlier about what is the surface of the sun? And that surface varies depending on what wavelength you're looking at. Depends on the elemental composition, the pressure, the density, all these things. But one thing that we still don't fully understand with stars are these features here. As an example, they're spicules. So this is jets of plasma that are always kind of moving up into space. And some of actually, we figured out that roughly 90% of the mass actually comes back down. But how does that mass flow change the exterior properties of the atmosphere? That's another question. I mean, there's a lot of quiescence, which means non-large flares happening. Quiescent solar physics and stellar physics, that's important because what I showed you here is that the atmosphere is about a million Kelvin, but it's always a million Kelvin. Even when there aren't lots of sunspots, even when there aren't these eruptions happening. These eruptions cause plasma to heat up to 10, 20, 30 megakelvin. As mentioned earlier, the core of the sun is roughly around 27, 28 megakelvin. These flares can be hotter than the core of the sun. With that being said, there's still a lot of things we don't understand when that's not happening, and you can actually see all these little features here. We still don't fully understand all that. And then when you look at other stars, which have different dynamics in their exterior, due to their interior being different, which I haven't even spoken about today, there's a plethora of scientific things that can be focused on and investigated. So stars are cool, especially the sun. So I want to thank you all for having me here. I appreciate it. And this was my first Astronomy on Tap, so hopefully you'll have me back again.
All right, let's give another big round of applause for both of our speakers tonight. And I'd like to point out that both Boston and Cambridge have Astronomy on Tap, and he came here first. Okay. So with that, our next Astronomy on Tap is the last Wednesday in November. That's the one after Thanksgiving, so I hope to see you at that one too. If you won trivia, please come get your prize. Otherwise, get home safe, and thank you so much for coming. Good job.